Your first test of the year, I'm going to start by going over format, so we're all clear as to what the format is. All right, so this is test 1. From your text, it's on 2.1 through 2.3. Now, recall, please, that prior to 2.1, we did also talk about other things. What are some of those other things that we talked about? What did we discuss before section 2.1, Frankie? Conversions. What else? What else? Zoe? Conversions, very good. That's the proper term, dimensional analysis, but conversions, same thing, good. Scientific notation. Good, good. Theo? We talked about, yes, and that's going to be embedded in 2.1 to 2.3. We're going to get to that in a sec. We did one other thing prior to 2.1 to 2.3. Actually, two other things, really.
Indirect.
Yeah, we talked about indirect and directly proportional. And then we also quickly, if you remember in your lab, went over graphing and lines of best fit. Okay, so given a certain set of data, being able to create a line of best fit with that data. Those are the 4 things we did prior to starting section 2.1. Okay, then section 2.1, 2.2, and 2.3. 2.1, well, let me think. What's the easiest approach? Let's start with 2.1 through 2.3, and then what I'm going to do is, if we have time at the end of the period, I'm going to come back and pick some of these topics to go over depending on what you guys want to look at out of these 4. I want to really focus on 2.1 to 2.3 because they're a lot more difficult than simple conversions and scientific notation, which you've seen already for several years now. So in 2.1, I'll just make a new slide for 2.1 real quick, okay? So these are the 4 main topics. Before 2.1, let's do this. Format of the test. Part 1 is going to be multiple choice. It's traditionally around 30% of your test. Part 2 is going to be short answer. Now, short answer involves either theoretical or mathematical stuff, but you're not going to have equations involved in part 2. So part 1, where you have multiple choice, it could be theoretical, it could be mathematical, you might need an equation, you're going to probably have to do a lot of analyzing graphs, position time graphs, velocity time graphs. Part 2, you want to focus mainly on short answer theoretical stuff. So I might ask you about direct versus indirect. I might ask you about acceleration on Earth and where it comes from. I might talk about constant velocity and what that means about acceleration. There's many theoretical things I could ask for part 2. Part 2 could also be some mathematical stuff I ask you, but you will not need a formula for part 2. Okay, you don't actually have to do any math. Maybe it'd be useful to know your formulas for part 2, sure, but they're on your formula sheet. Okay? Part 3, though, specifically, is going to be all using your formulas and your mathematical knowledge. So I call this free response, but it's really just mathematical. And that's 40% of your test. It's pretty much the exact same format for every test. Obviously, it's going to vary. Like one test, it might be like 35, 35, 30, or maybe it'll be like 35, 30, 35, whatever it may be, right? But it's generally around that kind of a setup. As far as time-wise for the class, most students end up taking most of the period. It's rare that people finish extremely early. If you're one of the, higher performing students in the class and know your stuff really well, you might finish like 5 minutes left in the period and have time to like check over a problem or 2. But as soon as you come in, you need to get started. If you forget a calculator, you're really going to be, up the creek without a paddle, big time. You're going to be just out of luck, huge. You need a calculator, please bring a pencil for the math part for the last part of the test. Okay, calculator and pencil for sure. The multiple choice and the theory part, you could do in pen is fine. I asked you to bring a pencil because I can't tell you how many times you have to make corrections on physics tests. Okay, so I don't want to see crossing off and then I can't read it and then I can't even give you points. Bring a pencil for the math part, please.
For extra time, do we just email you
Yeah, absolutely. So extra time, the way I work extra time is the following. I traditionally have students come either the period before or after to make up their extra time. If that's impossible, I do after. I never do before. Okay, because it gives them a look at the test beforehand. If you do extra time, though, you only get 4 out of the 6 pages. The other 2 you don't get to see. You get to see them after school. If you don't finish the 4 pages and you have extra time, you're stuck there. You cannot finish them after school. Once you've seen the question, you cannot, take an hour break and then come back and finish it. So if you do have extra time, you get, an extra half the period. So tomorrow's an A day, or Wednesday's an A day. AAABB, I think, is this week. So that means you'll get another 22.5 minutes on top. Okay? So again, if you get extra time, it's going to be a period afterward. Unless your period right before the test is free. I allow that. Because you can continue right into the test period. Okay, but again, if you have extra time, look at my schedule, look at your schedule, see when we have freeze in common. If it doesn't work out, we'll figure out when you're going to do it. Okay, but definitely email me. If I don't get an email from you the day before the actual test, at a minimum, I do not give extra time. So if you show up on the day of a test and you want extra time, it doesn't work. Okay, so please make sure you arrange ahead of time. I'm not going to make any exceptions whatsoever, just so we're all clear on that. Let's start with section 2.1 then, now that we've gotten through the nitty-gritty stuff. So 2.1 was about velocity, right? Displacement. We started using those two terms in 2.1. We also looked at speed and distance and the difference between those two. So let's begin with our formula so we understand where we're at. So the first formula we learned this year was V bar equals x over t. Okay, V bar meaning constant velocity equals displacement over time. Now it could also mean average velocity. If you know how far a person or an object has traveled, you could determine the average velocity by knowing its displacement over time. What is displacement? What is this term displacement? What does it really mean? What does x really mean?
How far you are from your position.
Good. Your change in position. Your change in position. It is not the path traveled. Remember, I could walk around the room, end up where I began, and my displacement is 0 meters. Because my position I started in is the same position I ended in. So I have no change in position by doing a circle. But by doing a circle, I have traveled some distance, which really takes into account the curve of the path traveled itself. Now, what formula involved distance when we had speed equals distance over time? Okay, the path traveled does matter when calculating speed. Speed is equal to distance over time. Again, V bar, I'll point to it so we're all clear. This location here, V bar, either means constant velocity or average velocity. But what do we assume when we use this formula? There's only one time we can use this formula. If blank, fill in the blank. If this condition is true, we can use this formula. What condition must be met to use this formula? We need to have a specific condition met in order to use this formula. A what? Not a direct route. Not a direct route. Because you could go over and then down, and your displacement would just be the hypotenuse then, so you could still figure it out. I like the idea though. There's one condition that has to be met. The other formulas we learned have what involved that this does not? Acceleration. So what condition must be met to assume to use this formula? When do we use it?
It's a constant speed.
Yeah, when we're either looking at a constant speed or we're trying to find the average velocity and we have nothing about the acceleration. Okay, so these are problems that do not involve acceleration. That's when you're going to utilize this formula. Okay? And they do not involve acceleration. So you ever going to use this formula for vertical motion?
No.
Why not?
Because you can't go vertically without acceleration.
Exactly. Gravity is always acting vertically, so there's always vertical acceleration. So you can't have vertical motion without acceleration. So this is only used for horizontal motion. Easy enough to remember that, right? Always used for horizontal. X stands for horizontal. Look at the formula. It's got x over t. Try and think of that. Now, you can have horizontal motion with acceleration, and if you do, you have to go to the other set of formulas. God bless. That's not a sneeze. Still. So if you have horizontal motion, you can have acceleration. This is not to say that you can't have horizontal motion without acceleration. But if you're using this formula, it's going to be horizontally. Okay, so let's look at those other formulas now. Let's look at those other formulas that we began using in section 2-2. And then we'll go to graphs in a little while. We'll start taking a look at graphs, the graphs that we made earlier.
Are we allowed to bring our formula sheet?
I give it to you. Yeah, I give you the formula sheet, so you don't even need it. But definitely take notes on your notability formula sheet, so when you're studying, you could look at that cumulative sheet throughout the year. 2-2, formulas, other three. What do we got? What do we got? There's three of them. Katie, one. VI plus AT. That's all right. Plus AT. VF equals VI plus AT. That's one. Yes, Theo?
VF squared equals VI squared plus 2x.
Now, write yourself a little note. Or that could be Y, remember. When is that Y? What kind of motion? Anybody? Vertical motion. Okay, horizontal is X, vertical is Y. And the last formula? Emma?
X equals VIT plus half AT squared.
And again, same thing is true here. That X could be Y as well, if it's vertical motion. What are some interesting things we should write down? When is VI 0? When is VI 0? It's very important that we know this. No. What does VI stand for, Pablo? V stands for velocity. What does the I stand for again? Not final. Not increase. Help them out, Matt. Initial. When is initial velocity going to be 0? When is VI 0?
When it's at rest, like it starts at rest.
When it starts at rest. If you hear a problem that says an object accelerates from rest, you should write these key words down, right? From rest, or at rest, starting at rest, or it's dropped. The minute you hear something is dropped, it means that it started at rest. You literally held it here, and you did this. You just let it go. So VI was 0 in that problem. So at rest, meaning starting at rest, or dropped from a certain height, you should jot down right now that VI is 0 in those problems. Now, you should also recognize, and this is really going into section 2.3 now as well. 2.1 and 2.2 and 2.3 are all similar ideas because we're looking at, displacement, velocity, acceleration, all of our kinematics here. So in 2.3 we talked about what happens when it gets to its max height. An object at max height, its velocity is 0. Another fact we should jot down. These are all facts that will help you in mathematical problems as well as earlier in the test. When an object reaches its maximum height, the velocity is 0. So as an object down here, it gets launched and makes it up to max height, the velocity up there is 0. Now, if you're looking at the first half of the problem, we call that VF, because it's the final velocity at the top. But if we're looking at the second half of the problem, where it's falling down, now it's what?
Yeah, it has a VI in this. Oh, it's negative.
Yeah, well, it's going to be negative, but the VF part and the VI we have to talk about. So on the way up, VI is some number, and VF would be 0. Now, fast forward in time. The object is now at the max height, and it's starting to fall back down. The same object. Now instead of VF, this is now VI is 0. And we're going to figure out VF is some value on the way back down. And these, if there's symmetry in the problem, will be opposites. We proved that in class, if you recall. We talked about a problem where a rocket was launched with an initial velocity of 25 meters per second, and it returned to ground level. We eventually solved and figured out that the final velocity was negative 25 meters per second, which made sense. It gained all the energy that the object lost on the way up. The potential energy, it gained it all back on the way to kinetic energy. And we're going to talk about energy in chapter 5, but just to give you an idea of why this is true. So again, the first half of the problem is on the left-hand side of the screen. the second half of the problem is on the right-hand side of the screen. This is for a symmetric problem. Okay? For a problem like the one Sierra asked about from your homework from 2-3, this approach cannot necessarily be used because then it's not going to be symmetric. The other problem, it started, right? Remember the one she asked about, it started at some height, like it started on a cliff right here, and it was launched up, and then it came back down all the way back to the ground. So there is not perfect symmetry in a problem like that. Okay, there is not perfect symmetry in that problem. Let's take a minute to look at graphs. You really need to know your graphs, so I want to make sure we emphasize that. First, we had a position versus time graph. And then we had a velocity versus time graph. Now, tomorrow when we have the double period lab, we'll definitely, the double period lab is all about graphs and motion. And we're going to use a little motion detector to describe the motion of somebody and when they move, what happens to their position. But I want to make sure that we're clear today because we're reviewing as to what this means. So, I'm going to draw a graph, okay? I'm going to say that this is what's occurring. Okay, that's the graph of the position versus time. So what could you tell me about this first section of time? So I'm going to put like here, let's say this is 2 seconds in, 5 seconds in, 6 seconds in, and 8 seconds in. Let me erase this, make this look clearer. Okay? So, from 0 to 2 seconds, give me something. Give me some piece of information. If I ask you just describe the motion of this object based on the graph. Theo, from 0 to 2 seconds.
You're moving away from the origin.
Good. Now, where did you start, Theo? Did you start at the origin?
No.
No. So if the origin is the motion detector, remember it's like a number line.
You're moving farther away.
Good. So you start some distance away, which we don't know, right? Whatever the height on the y-axis is. Let's say this is 1 meter. Okay? You start a meter away from the origin, and you move away from the origin. Okay, once you get after 2 seconds, what do you do then?
Stop moving.
You stop moving for how long, Ant?
From 2 seconds to 6 seconds, so.
Well, to 5, sorry, it's not clear.
5.
From 2 to 5 seconds, you're not moving. So if I'm describing the motion of this graph, I start with, you start a meter away from the origin, you move away from the origin until you're, say, 3 meters away. I'm just going to pick random numbers here for now. Then you stop at 3 meters from the origin for 3 seconds. Then what do you do next? From 5 to 6 seconds. From 5 to 6 seconds, what do you do? Honor? Goes down. What does down mean, though? Remember, this is not y-axis anymore. This is horizontal motion that's going on here. So again, you start a meter away from the origin. You move away from the origin for 2 seconds to 3 meters. You wait there for 3 seconds. Then what do you do?
I actually have a question. From 2 to 5 seconds, can't you still be moving though?
No, because your position is the same. X is position, right?
Yeah.
What does a flat line mean? It means they're the same the whole time, right?
Only move.
Whenever it's a flat line for position, when it's a flat line for velocity, you're still moving with a constant velocity. We'll talk about that graph over here in a moment. But remember, if you have a flat line, it literally means you're standing at 3 meters for 3 seconds. I'm literally standing 3 meters from the origin for 3 seconds. Then between 5 and 6 seconds, I go from 3 meters back to 0 meters. But 0 meters is like the origin. I have to go back there. So in the next second, I have to hurry back here in 1 second from 5 to 6 seconds. Now I'm back at the origin at 6 seconds. So I ran back with what kind of a velocity? If I'm moving left, what kind of velocity is that? Negative. And I know it's negative because the slope of this line is negative, isn't it? Remember we talked about the slope of the line being velocity for this graph? You got to really recall this information. So you move away from the origin, again, with a positive velocity for 2 seconds, because the slope is positive. Then the slope is a flat line, which is 0 slope, so you have 0 velocity, so you're not moving for 3 seconds. Then you run back to the origin in 1 second. Then what happens after that? From 6 to 8 seconds, From 6 to 8 seconds, what happens? What kind of displacement do you now have? You have a negative displacement, so you have to move this way now. So you've not only gotten back to the origin at 6 seconds, but now you're moving to the left for the last 2 seconds with some negative velocity. You're moving past the origin. Okay, so that's how I would describe this graph. Some note you will write down, you should write down along the way that velocity is positive here. Velocity is 0. Velocity is negative. And here again, velocity is negative. How do you know that? Because velocity is equal to the slope. Remember, the slope of a position versus time graph is velocity. It is velocity. If that's not clear, just think about how you would calculate the slope. You'd find the change in the vertical variable, which is delta x, over the change in the horizontal, which is delta t. Delta x over delta t is what velocity is. Recall that velocity is the change in an object's position over a time period. This here that I'm circling, that's the slope. It's the change in the vertical component over the change in the horizontal component. And you're taught so often in your math classes that slope is change in y over change in x. Forget the label y and x. Just think change in vertical over change in horizontal. Okay, so stop memorizing slope as change in y over x, because it throws you off when suddenly the y-axis or the vertical axis is labeled with an x on it. So if I wanted to find the slope, I would find the change in position over the change in time. Okay, so what would the slope be? What would the slope be for the first part? And I'll point to it. For this part right here. What would the slope be in this segment? What's the change in the vertical component? How much does this go up by? Everybody can do this. What's the change from here to here? So the change in the x, which is this, is 2, over a time period of 2, which makes your velocity simply 1 meter per second. So you could literally tell me the velocity from 0 to 2 seconds just by analyzing the graph and finding the slope. What's the velocity here again? Because it's a flat line. Remember, flat line slope is 0. How about here? What's the change in the position? It goes from 3 meters to 0 meters. -3. Remember, you're here, and now you're moving in the negative direction. So I've got a -3 divided by how much time elapses from 5 to 6? 1 second. So the slope here is -3. And then here we don't know because we didn't give another dimension down here. So we're not sure what the slope is exactly. But remember, change in the vertical component over change in the horizontal component is slope. And if you look at that, that's why velocity is slope. Because it's x over t. Vertical over horizontal. Now, if I look at the slope of this next graph on the right, the vertical variable is now what? What's the vertical axis labeled as? Velocity. And the horizontal is? If I have velocity over time, who remembers what's change in velocity over time defined as? Change in velocity. You have to have what if you have a change in your velocity? Good. It is the slope, yep. But specifically, give me a term for this. Acceleration. So in this second case, acceleration is the slope. This is why when we went over these, I said to you, they're very similar, right? You see the similarities? But one of them on the left here is our position time, which uses velocity as a slope. But when we look at velocity time on the right, the slope is acceleration. So for a graph like that, let's take a look at this. I'm going to use yellow. Here's my graph. Okay, I'm not going to give numbers for now. We'll call each segment a different letter. So segment A, segment B, segment C, segment D, E, and F. Okay? Yeah?
Why is it delta V instead of just V?
Change in velocity, just like change in position. Like how did we, remember earlier, Klaus, over here? When I wanted to find the slope of this line over here, I found the difference between these two. I did 3 minus 1. It's really delta x up here. I just dropped the delta a lot. It's just me being, whatever, inconsistent. I guess I should be more consistent. It's the change in position. So it's still change, okay? Remember, delta means change whenever you see the delta there. So for this graph on the right, this velocity graph, can somebody describe the motion in section A? In section A, what is the motion like? I'm seeing the same two hands a lot. Come on, other people want to see from. In section A, describe the motion. Describe the motion. Sierra. Very good. The velocity is 0. Think about it. If you're along the horizontal axis, it means that you're at a height on the y-axis of 0. So the velocity is 0 at the beginning. So we've got no velocity here. So I'm standing still for whatever time this is, say 2 seconds. Then what do I start to do? Katie? Then I start to increase velocity. My velocity gets faster. It gets faster, it gets faster, it gets faster until it reaches its fastest velocity. Right? At this point right here, I've reached my fastest velocity. Now, after section B, after I've increased my velocity, therefore there must be acceleration here, because acceleration is the slope. What kind of slope is this? So there's positive acceleration, which makes sense. Didn't I get faster? That's positive acceleration. Then at part C right here, what happens? Yeah, I start to continue to move, but I have no acceleration. If I have no acceleration, what kind of velocity do I have? Constant velocity. Guys, again, you only have 0 velocity if you have a flat line on a position graph over here, or if your velocity is literally on the x-axis, that means your velocity is 0. Like right here, the velocity is 0 also. At that exact instant, the velocity is 0 as well. But up here, doesn't this have some height? Pick a number for the y-axis here. For the, what number? 3. So if this is 3, okay, 3 meters per second. If that's 3 right there, it means that I've gone with no velocity for a little while. I've accelerated, got it faster and faster to get to 3 meters per second. I don't stop. I'm pausing because I'm literally like freeze framing, but I'm not literally stopping. I get to 3 meters per second, right? So let me do that again. And watch what I continue doing. So I pick up speed, get to 3 meters per second, and then stay at that rate for a while. Then, what happens after that? I start to decrease my velocity until I get to 0 velocity. So it's difficult for me to act this out in the front of the room. Let me try it one more time because I'm running out of room. So I stand still, I stand still, I stand still. I get faster, I get faster, I get faster until I get to my max velocity. I stay at that max velocity for a couple seconds. I then slow down, I slow down, I slow down, I slow down, I slow down, and then I stop. Then what kind of velocity do I have when it's down here? Negative velocity. That means I move to the left. So I literally stop about face right here. I start to move with negative velocity. I get faster and faster and faster in the negative direction until I reach my max negative velocity. God bless you. Until I reach my max negative velocity, maybe right here, and then I coast at that negative velocity for a while. But this portion F and portion C, look at portion F and C. They're pretty much the same thing. They're both constant velocity, except one is negative and one is positive. So here you've got acceleration is positive. Here acceleration is negative. Acceleration is negative. Here acceleration is 0. So velocity is a constant. And happens to be positive here. Here acceleration is 0. So the velocity is again a constant. But it's a negative velocity down there. So each portion of the graph represents a different type of motion. So I'm giving you a graph and asking you to tell me the motion. I could also give you maybe 3 sentences and tell you draw a graph based on what I'm telling you. If I say the person is not moving, and then they move with this much velocity, and then they stop for this many seconds, and they move back, that's the kind of practice you want to be working on. Now tomorrow your lab is all on this stuff. Okay, so we're going to act it all out. We're going to have a double period. You're going to have more time to practice more of these graphs as well. The actual parts of the lab you're going to see are going to be literally just like this, where I give you a graph, tell you to describe the motion, or vice versa. I give you some motion and tell you to draw me a graph exhibiting that motion. Okay? The difficult part that most students run into here, and I'm telling you right now, it happens every year, is that they mix up these two graphs. They're very different. Position versus time is different from velocity versus time. So a lot of the time on a test, you need to make sure you look to see what your labels are. If you see along the vertical axis the letter V, now you're on a velocity time graph. But if you see an X or the word position along the vertical axis, you're on a position versus time graph. You need to make sure you know which graph you're working with on the test. Both types of graphs will be on the test. I guarantee you 100%. Okay, so you need to be able to understand that there's a difference between these two types of graphs. Let's do it.
Negative on this one is velocity or positive velocity.
On the one on the left
Yeah.
here? Yes.
So that, and then that one's acceleration.
Absolutely. Absolutely. So remember, the slope for the first graph is velocity, but the slope for a velocity graph can't be velocity, right?
Yeah.
So if you remember that the slope for a position graph is velocity, then you should kind of know that velocity becomes acceleration, because that's your step stool. You have displacement, velocity, acceleration. Those are the three things that we learned about. So if you remember that this slope is velocity, that one's got to be acceleration. Okay? Let's say the following. You could write it down, or you could just listen to what I'm going to tell you. Let's say that an object is thrown downward. An object is thrown downward from a windowsill. An object is thrown downward from a windowsill, and it travels 25 meters before striking the ground. Travels 25 meters before striking the ground. Determine the initial velocity if the final velocity is 200 meters per second. Determine the initial velocity if the final velocity is 200 meters per second. Part B would be, how long does this take? So expect two-part problems again. How long does this take would be part B. All right, so we want the initial velocity. If it hits the ground, I'm using too nice of words in class sometimes, I realize, because in the test it's even tougher. So I would probably say this actually. I would probably say determine the velocity when the person releases it or throws it. If the impact velocity when it hits the ground, or impact velocity, is 200 meters per second. You need to know that impact velocity means the velocity right before it hits the ground. That's final velocity. Okay? These terms that I utilize in class are very important. Determine the initial velocity if the impact velocity is 200 meters per second. Give me some piece of information to start. Remember, givens always first. It's not the same, absolutely not. Yeah, it's not the same. Remember, being dropped literally means VI is 0. We're trying to find out VI in this problem, so it's not going to be 0. Theo, give me a piece of information.
Well, final velocity equals 200 meters per second.
200?
Is that what you said?
Yeah, but is that right?
Yeah.
Are we sure? Yeah, 100%?
Clearly not. Yeah, I seen it 6 times.
What piece is he forgetting? Come on, guys.
Acceleration.
What is it?
Negative.
Good, Willow. Negative 200 meters per second. Now, that's the tricky stuff, guys. Remember, if I tell you impact velocity, or I need to say impact speed is 200 meters per second, you need to know that because it's moving down, its final velocity is negative. Okay, be careful with that. What else? What else?
The initial velocity is 0.
No. Remember, I don't just ask that. You got to focus. If it's dropped, initial velocity is 0. Remember, this problem, it says the object is thrown downward, literally thrown, like you spike a football, throwing it downward.
But doesn't it start at 0?
No, because, ready, watch. The whole time my hand is on it, it's getting faster. When I release it, it's got velocity already. This is different. See that? That starts from 0. Y equals 25 meters per second? Meters, but what else? Thank you. Negative. Good, class. Okay, good combination there. 25 is definitely Y, but make sure our units are correct, and we know that we're moving downward, so the displacement must be negative. What else? The last piece of info that we always know for vertical motion?
Gravity.
Good. Okay, we always know gravity. It's the same thing for all of these problems. So we've got enough information to solve for what we're looking for. Remember, part A was find the velocity with which the person threw, and part B was how long does it take. We've got enough info for both of these parts. Formula. For part A, what should the formula be? Nat.
Vx squared equals vi squared plus 2ay.
Very good. And our goal is going to be solved for VI, correct? So I'm going to subtract 2AY from the whole thing. Remember, think about 2AY as a number. Again, think about 2AY. Since you know A and you know Y, think of this whole thing as a number. How would you get rid of it mathematically? You would subtract. And then just take the square root to get your VI. You cannot cancel a square root and a square if there's a sum or a difference under the radical. Again, you cannot cancel this square here with the square root because there's a sum or a difference here under the radical. Please make sure you don't cancel that. So you're going to plug in negative 200 squared, which is going to be positive 40,000. 40,000 or 400,000? 40,000, right? Should have 4 zeros. Remembering that there's a plus or minus out front of the radical. Minus 2 times negative 9.81 times negative 25. It's all going to go into the radical. In the second part, to find time, you'll know VF, you'll know VI, you know A. Use this for the second one. Okay, you'll get VI from that calculation right here. VI is definitely negative because you're throwing downward. So tomorrow we're going to take up with the lab. If we have time in the second period tomorrow, what I will do is I'll do a little more review and post a little bit more of a video. So I'm going to post this tonight for the class.